Hello and welcome to Chapter 7.2 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter we're going to be estimating a population mean from a sample mean by creating a confidence interval. And in this particular chapter we're going to make the sort of unusual assumption that sigma is known. And sigma is the population standard deviation. And so it's not necessarily going to happen in real life. If you don't know the mean, it's unlikely that you'll know the population standard deviation. But in this case, we're going to assume that it is known because this helps develop the procedure for building a confidence interval. In the next two sections, we'll get into more realistic circumstances. So that's going to be the case here. We're going to assume that we know the population standard deviation. In addition to building confidence intervals, we're also going to determine a minimum sample size required to reach a certain degree of accuracy in our interval estimation. All right, so let's get started. If you recall from the previous chapter, 7.1, the critical phase of constructing one of these confidence intervals is determining the margin of error, right? It's this thing here. All right. Once we get the margin of error, we're really quite set because then we just take the sample mean, subtract the margin of error, and the sample mean, and add a margin of error, right? So that's sort of the key, but the margin of error has all these, other parts. So we're going to get into this in some detail right now. Okay, so there's the margin of error. We'll get to that last. So when we do these population estimates for a mean, mu will denote the population mean. That is what we don't know. We're trying to estimate it. X bar is the sample mean, right? That's the one we have. It is also called the point estimate. So if you were required to just give a single number to estimate the population mean, you'd use the sample mean. Little n is the sample size. Sigma is the population standard deviation. And again, in this particular section, we're going to assume that that is known. The confidence level, which is usually 90, 95, or 99%, it technically represents the success rate of the procedure. How often the actual population mean will be within the interval we get. It defines the confidence that we have in that interval. Alpha is 1 minus the confidence level in decimal form, right? It also represents the area in the tails. If you go back to sort of developing one of these confidence intervals, alpha represents the combined area in these two tails, right? So if we have the middle 95% here for a 95% confidence interval, alpha is 0.05. And if you divide that in half, that's the area in each tail, right? Okay. So, and z sub alpha over 2 represents the critical value. We call these critical values of z's used to calculate the margin of error. And what that does, going back to the previous setup, it delineates the middle 95% or whatever your confidence level is for the sample means. Okay. So z sub alpha over 2, there's really no division. This is just a name, and the alpha over 2 describes what the critical value stands for. All right, so we go to the margin of error. This formula here. And it's the same formula we derived in the previous section. And it's just the critical value, right there, times the population standard deviation divided by the square root of n. So that's our margin of error. And before we proceed, there are a few requirements. If you're dealing with a sample, it should be a simple random sample. Right? We really shouldn't be clustering or stratifying these things, and we certainly want a good random sample, at least for starters. The value of the population standard deviation, sigma, is known. Right? And in practice, that is unlikely to be the case, but it helps us in a few ways as we proceed through this particular chapter. The sample size, n, is greater than 30 or the population is normally distributed. actually and or. You can have both if you'd like. So if you know that the population is normally distributed, you can use small sample sizes. But if you don't know that the population is normally distributed, you need a sample size of 30 or bigger. All right, so here's the procedure. And again, we're going to look, we need to calculate this margin of error. So the first thing we're going to do is determine the critical value of z, which we just call z sub alpha over 2. And if it's one of our popular values, we have a nice little cheat sheet at the bottom of the z table. And that is down, actually it's at the bottom of each. It's below each z table. So that's right here. So here's our confidence levels, our popular confidence levels, and here are the associated critical values of z. If you don't have one of those popular values, you have to take alpha, divide it in half, put it into each tail, and look for that inside the z table to find the corresponding value of z. It's not particularly difficult, but it's a little more time consuming. So we will usually be dealing with one of these popular confidence intervals. Then you want to calculate the margin of error using this equation right up here, right? 7.3. You determine the confidence interval by taking the sample mean, subtracting a margin of error, sample mean, adding a margin of error, and then sticking mu in between. So that tells us we suspect that the population mean is between those two values. And then you write an understandable concluding statement that sounds like I am blank percent, maybe 95% confident that the mean, something say pulse rate for all, something say men, is between, and this is where you put in your interval estimates, right? The upper and lower bounds of that interval. Round-off rules, when you're using raw data, you use one more decimal place than the raw data, just as in the round-off rule for the mean or the standard deviation. If you only have the sample mean, you want to use the same number of decimals in your interval estimate as you do for x bar. And a little helpful hint here, when you're calculating this margin of error with this formula here, I usually carry that out to an extra decimal place or two before I add it or subtract it to the sample mean, just so that I don't get any loss of precision in the calculation process. And then when you finally get your final answer for the interval, then I round to one more decimal place than the data or the same number for x bar. So when you're doing your calculations, it's good to carry your calculations out to a couple extra decimal places. All right, first example. This example is actually the same as the example in the introduction. I have a simple random sample of 35 men, so that's good. 35, it's bigger than 30, so I don't really have to worry about the population being normally distributed. And from that sample, I get a mean pulse rate of 72.5 beats per minute. And I will assume that the standard deviation for the population is 10.2. So somehow or another, I know that sigma is 10.2. Right? So let's get started. And I'll put the preliminary information here just to sort of help us so we don't have to look back at the paragraph. The sample mean, 72.5. The population standard deviation is 10.2, and the sample size is 35. To find our critical value of z, since this is a 0.95 confidence level, or a 95% confidence level, I go back to my table, and that's one of the popular ones. So there's my 0.95. So the critical value right there is 1.96. That's z sub alpha over 2. Or you know what? I'm going to switch to full screen mode. Okay. And I'm going to... There we go. We got a little more space to work with here. Okay. So our z sub alpha over 2 that we just looked up is 1.96. Then I need the population standard deviation divided by the square root of n. When I do that, I get 3.38. Right? So that is my margin of error. So I have a sample mean and a margin of error. So that's enough to build my confidence interval. The lower limit is the sample mean minus 3.38, which is 69.12. The upper limit is the sample mean plus the margin of error, that's 75.88. And then rounding to 1 decimal place as the sample mean is, I get a confidence interval where mu is between 69.1 and 75.9. So you get all done with that, and you may wonder, what have I done? I've followed all the rules. So here's what you've done. The concluding statement is very important. I am 95% confident that the mean pulse rate for all men, right? I'm talking about the population of all men, is between 69.1 and 75.9 beats per minute. Right? So that's what we have done. And in the your turn problem, it's the same problem, only I want you to find the 99% confidence interval estimate. Right? So we start off with the critical value of z. Since 0.99 is one of our popular confidence levels, I go here, and it is, I better get this in full screen too. So now I'm at the 0.99 confidence level, so my critical value got a little bigger to 2.575. So that's where the 2.575 comes from. Right? And the margin of error is given by our formula for the margin of error. There's the critical value, population standard deviation, square root of n. When you plug in all those numbers, you get 4.44. And notice our margin of error got bigger. This was at the 95% confidence level. We came up with 3.38 for the margin of error. And at the 99% confidence level, it's 4.44. So our margin of error got bigger. Creating the confidence interval is very simple. I find the lower limit by taking the sample mean minus the margin of error. It's 68.06. The upper limit is found by taking the sample mean and adding a margin of error, 76.94. And the confidence interval, I just take my upper and lower limits, round them to 1 decimal place. There's the lower limit and the upper limit, and I stick mu in between, signifying that my estimate is that mu is between 68.1 and 76.9. Concluding statement, I am 99% confident that the mean pulse rate for all men, again that's important, is between 68.1 and 76.9 beats per minute. I want to draw your attention to part C here. What happens to the size of the confidence interval as you increase the confidence level? Well, notice, at the 95%, so this is our 99%, the 95% interval was mu is between 69.1 and 75.9. So when I was 95% confident, this was my interval. And when I got more confident, my interval, 68.1 to 76.9, got bigger. So as you increase confidence, the interval gets bigger. And that's basically because the margin of error got bigger. And that's an important relationship, because a lot of people think, you know, a lack of accuracy means you're uncertain about it. But in fact, it works the opposite way. Confidence and accuracy are inversely related. All right. If your confidence level goes up, your accuracy is going to go down, right? If you want me to be more confident in a statement, I just broaden my estimate, and I'm more confident that it's true, right? So confidence and accuracy are not the same. In fact, they work inversely. Okay, so calculating a sample size. So here's the setup for this. Suppose I got to this problem here, right? I'm 99% confident, and I get a confidence interval of 68.1 to 76.9. And I say, that's too big. I can't tolerate that kind of accuracy. I need something smaller. I want to say, you know, my margin of error is too big here, right? this margin of error is too big. I don't like how that worked out. Say I want a max equal to 2. I want a margin of error no bigger than 2. So the problem is with this particular data, I can't do anything. It's, my margin of error is what it is, and I can't change it. So I have to go back and take another sample, and the key thing to do is make my sample bigger. Right? How much bigger do I have to make my sample size so that my margin of error gets smaller? Right? And so that's what this second part of this chapter tells us. Right? Suppose we want a confidence interval associated with a particular confidence level and a bound on the margin of error. Can we determine the appropriate sample size? And the answer is yes. And it's really not that hard. If we go back to the margin of error, the formula for that, if we solve that for n, we get this formula. N is equal to the critical value, population standard deviation, divided by the margin of error, all squared. Right? Don't forget the squared, popular mistake. So that gives us our sample size. Specifically, it gives us a minimum sample size for a required upper bound. So this upper bound on the margin of error is this thing. So I put in the maximum margin of error that I'm willing to tolerate into this formula, and that'll give me my sample size. And the interesting thing here is that the sample size, the minimum sample size, did not depend on the population size. A lot of people will think, in order to have a sample mean that accurately reflects the population mean, you need to sample a certain percentage of the population. And it's actually not true. You might need a very large sample size, but it's not related to, there's no minimum percentage required in order to have a valid estimate. A little round-off rule. It's not really a round-off rule. If 7.4, if this equation does not result in a whole number, if you get a decimal, you use the next larger whole number. In other words, you round up. You always round up when you're using this formula for the sample size. And again, this is actually a very practical thing, but again, there's a very good chance we won't know sigma. So if we don't know sigma, what do? Well, you can start off, if you have the raw data, you might be able to take the range of all your data and divide it by 4. That's one estimate. If you can find a standard deviation for a similar population, you can use that. But the trick is to approximate large. Right? You want to approximate large on this, because otherwise, if you don't approximate large on your population standard deviation, you might wind up with too small of a sample size. Right? So as long as you approximate large, everything should be okay. Okay, so let's look at an example about calculating a sample size. And it's sort of a continuation of the example 1. In a prior sample of 35 randomly selected men, we had a mean pulse rate of 72.5 beats per minute, and the standard deviation of the population was 10.2. I want to estimate the pulse rates of male marathon runners. Male marathon runners. Right? How many marathon runners should I select if I want to be 90% confident that the sample mean is within 1.5 beats per minute of the population mean? So what this 1.5 beats per minute, that 1.5 is the maximum margin of error. Right? That's the error I'm willing to tolerate. Max margin of error. Right? And we're going to set that equal to E in my equation. Okay, but if you look at my formula above, and I rewrote it here for convenience, so I have E, that's 1.5. I can get Z sub alpha over 2, but I don't have the population standard deviation for the heart rates of all marathon runners, right? But I do have the standard deviation from a previous study of 35 men. So that's 10.2 is the standard deviation, and that's for just adult men. Here I'm studying male marathon runners, adult male marathon runners. So I can assume that the standard deviation for that subgroup of men is about the same as for all adult men. And in fact, it's probably smaller because it's sort of a tighter group. It's a subset of my population of all men. So I'm willing to bet that the actual population standard deviation for marathon runners is less than 10.2. But I'm going to use 10.2 even though it's too big, because estimating too big is all right. We want to estimate large on the population standard deviation. Okay, so I have my margin of error is 1.5. My population standard deviation is 10.2. I need my critical value of z here, right? And I'm looking at the 90% confidence level. Luckily, that's one of our popular values. So I go to my table. At the 90% confidence level, my critical value is 1.645. So I go to 1.645. So that's where this came from. 1.645. So I plug all that into my calculator. I get a minimum sample size of 125.1. So I need to have at least 125.1 marathon runners in my sample. But if I have to have at least 125.1, I need to select at least 126. So I'm rounding up, right? So if my formula for the sample size winds up as a decimal, I round up to the next integer, right? And if I do that, and I get my sample, and I get the mean from my sample, I can be pretty certain that my margin of error will be 1.5 or smaller. Right? Let's do your turn. How many male marathon runners should I select if I want to be 99% confident? So notice, I want to get more confident, and I want the sample mean to be within 1 beat per minute of the population mean. So this 1 beat per minute means that my max margin of error is 1. Right? So my margin of error is now 1. I'm going to keep the same population standard deviation based on the reasoning from the previous example. But now I'm at the 99% confidence level, so my z sub alpha over 2 changes. When I go to my table, z sub alpha over 2 at the 99% confidence level is 2.575. So that changes. Z sub alpha over 2, 2.575. And when I do that, plug all that stuff, there's my 2.575. I plug that in, square it, don't forget to square it. I get 689.85. And again, I need to round up, because I need at least 689.85, so I need 690 runners for my sample. And if I get 690, I will be, I'm pretty certain that my margin of error will be less than or equal to 1. Right? And notice, I got more confident, and my tolerable margin of error got smaller. So my number from here to here got a lot bigger. Got bigger for 2 reasons. One, I increased my confidence level, and the other, I decreased my margin of error. Right? So I believe that wraps up chapter 7.1. I will see you again in 7.2. All right. See you later.